we're going to talk about motion types now. You went over uniform motion a lot in Science 10, so we're going to focus a little bit more on non-uniform motion in Physics 20, but we're still actually going to go over uniform motion because it is important. Sometimes the velocity of an object is actually constant, and that's what uniform motion tells us. So that's when acceleration is 0, because of course acceleration is the rate of change of the velocity. So if the velocity is constant, if it's not changing, then obviously acceleration is 0. So that is when we see this nice straight line on a distance time graph, okay? So if you see that, we know there is constant acceleration or constant velocity and therefore no acceleration. Non-uniform motion is, of course, when velocity is changing. So that's when acceleration isn't 0 because, of course, if acceleration is the rate at which velocity changes, and velocity is changing, acceleration cannot be 0. So often when you see a curved line like this on a distance time graph, when it has a nice constant curve like that, that is some nice non-uniform motion where the acceleration is changing constantly, and if it's kind of jagged or something like that, it still means that it's non-uniform motion. So uniform motion only happens when there's nice straight lines on a distance time graph. So let's talk about uniform motion involving instantaneous acceleration, which obviously doesn't happen, but say acceleration is fast enough or deceleration is fast enough that we can basically consider it instantaneous. So this is when we have a graph like this, where the velocity really quickly changes right there, right? It goes from having a slope to having a slope of 0, being completely horizontal. So even though in a graph like this, the segments are uniform motion, so this segment right here, that's uniform motion, right? This segment right here, this horizontal bit, that's uniform motion. But if we look at the whole graph overall, it's actually non-uniform, okay? And so we're considering just this instant acceleration at these points where the line changes direction. So we're saying it instantaneously stops and instantaneously has velocity again, which doesn't happen, but again, if it happens fast enough, we can say it's close to instantaneous and just consider it that way, okay? And it just makes the math a little bit easier, which is nice for us. So when we have something like this, where we do have non-uniform motion, but we have points of uniform motion within that, we can calculate average distance, or average speed and average velocity. I cannot tell you enough that this truly is an average, okay? So is this going to tell us the speed at any one point? No, it's giving us the average for the entirety of the motion, and that is so important that you understand that. So what is average speed? It's the total distance over the total time, okay? That's how we find average speed. So if I want this, I want the total displacement, or the total distance that it goes, divided by the amount of time it takes, which would be 60 seconds, okay? If I want average velocity, it's total displacement over time, total time, right? And that's the difference between velocity and speed, right? Because velocity is a vector, so we need the other vector, we need displacement. Speed is not a vector, so we need distance, which is also not a vector. Those are scalars, okay? Just a really quick note here. A lot of people want to find average speed or average velocity by finding the speeds or the velocity at each point of a graph like this, and then averaging them. You absolutely cannot do that. That is not finding average, because that's not accounting for the fact that you might have different time intervals, right? So here it has a positive velocity for 10 seconds, and then it rests for 40 seconds. So we can't think of those two things as equal. Therefore, we can't just average it by adding them all together and dividing by how many velocities you have. You absolutely cannot do that. That's why we just need total distance over the total amount of time that something took, okay, for average velocity. So let's determine the average speed and average velocity for this graph that I showed you just before this. Okay, so if we're going to do that, let's start with average speed. That's just v. So remember, it's the total distance over the total amount of time that it takes. Okay, so let's look at the distance. So from here to here we go 10 meters. Okay, from here to here, guess how far we go? 0 meters. From here to here, it goes from 10 to 15, so that's an extra 5 meters. And then from here to here, yeah, sure, it's going backwards, but that's still traveling 15 meters. And since we don't care about direction, that's not going to really do much for us. And that's happening over a total time of 60 seconds. So if we calculate that, we should get that our speed is equal to 0.50 meters per second. Okay, and that is the average speed. Does that mean that any point along its journey it's actually going 0.50 meters per second? No, it just means that's its average over this entire motion. Okay, so let's go on to average velocity, not average speed, because it will change, right? If I want average velocity, I need total displacement over the total amount of time it takes. So how is that different? That's different because direction matters. So displacement, what is that? That's how far it is, the ending point is from the starting point. Guess what? We start at 0, we end at 0. What's the displacement? It's 0. Okay? It ended at its starting point. So therefore displacement 0. Total time is 60 seconds, but of course, 0 divided by anything is just 0. So our average velocity in this case is 0 meters per second. And again, that's how you differentiate between velocity and speed. Velocity, we need that displacement over time. Speed, we need distance over time. Let's do one more with average speed and velocity. So we have a car driving 80 kilometers per hour west for 2 hours, stops for 20 minutes, turns towards the east and drives 60 kilometers in 35 minutes. Okay. So, first of all, let's look, we have kilometers per hour and kilometers and minutes and hours. So we just need, usually we go to meters per second. Here I'm actually going to tell you it's okay to keep things as kilometers per hour at this point. Let's just look at things in terms of kilometers and hours and minutes, and make sure that we, at some point, make sure all those minutes and those hours are the same, right? We only want one unit. We don't want a bunch of different units for time. That can't happen. Okay, so we know that the car is driving 80 kilometers west for 2 hours. So that didn't actually give us the distance it went. So that's also another problem. Then we know it goes 0 meters for 20 minutes, and then we know it goes 60 kilometers in 35 minutes. So one other problem we have here is we can't actually find the total distance at this point because we need to find the distance for this little bit. It gave us enough information to find the distance, but we need to actually find it. How do we do that? Well, we know velocity is equal to distance over time, so therefore distance is equal to velocity times time, if you just rearrange that. So that's what we're going to start by finding, is finding that distance that it actually goes on the first leg of its journey. So let's do that. So distance is equal to velocity times time. So my velocity is 80 kilometers per hour, and the time is 2 hours. Now it's okay that I'm using kilometers per hour and hours here, because again, the hours is kilometers per hour, 2 hours. If I was using minutes, then that would be a problem. That altogether is 160 kilometers. And just because I am a bit of a stickler, we do want meters per second as much as possible. So I'm going to convert this to meters. I'm going to start converting everything to meters and start to think of things as that. So if I convert that to meters, I just need to multiply it by 1,000. and I get 1.60 times 10 to, the 5 meters. Okay? So there's my distance for the first leg of the journey, and then for the second leg it's 0 meters, and then for the third it's 60 kilometers or 60,000 meters. Okay? So let's keep going with that. So let's find our average average speed here. So remember, total distance over total time. Okay, and let's take a look at what exactly that is. So total distance, well, we go 1.6 times 10 to the 5 meters, and then they go 0 meters, and then they go 60,000 or 6.0 times 10 to the 4 meters. Okay? So that's their total distance. Remember, I don't care about the east and west and all that fun stuff because this is just distance. And then over total time. Okay, so I don't want hours and minutes. I just want 1 unit. And since I said I'm going to try to do meters per second, then I want to convert all these things to seconds. And I'm going to do that right in this fraction here. Obviously, I'm going to do that separately when I actually calculate it. But we got 2 hours. I want that in seconds. So I multiply that by 3,600 because I know there's 3,600 seconds per 1 hour. Okay, and then we have 20 minutes, and I want to convert that to seconds. How do I do that? Well, 20 minutes, we know that there is 60 seconds per 1 minute, so we multiply it by 60. And then finally, that last 35 minutes, and we're going to do the same thing there. We're going to multiply it by 60 because, again, we know that there's 60 seconds in 1 minute. So that, there we go, is converting them all to seconds. So I'm going to do that separately on another line when I'm doing that in my calculator. Okay, and I'm going to find the total time, and then I'm going to take 1.6 times 10 to the 5 plus 6.0 times 10 to the 4 and divide it by that number that I got for the time. And when we do that, we get 21 meters per second. Okay, so there's our average speed. And now we got to find our average velocity and see if it's different, which we know it will be because they're going different directions, right? So here we have it going west for a bit, and then we have it going east for a bit, okay? So the question is it going further west or further east? It looks like it's going further west, so we know it's going to end up west. So remember, you don't have to always have east as positive. I can go ahead and say, I'm going to go ahead and define west as positive, because guess what? I feel like it. Okay, so that's what I'm going to do, and that means anything going east should be negative. Okay, so now we're going to do average velocity, and remember that's total displacement over time, over the total time. Okay, so it's going to look a lot like the one that I just did. The 1.6 times 10 to the 5 meters, or the 160 kilometers, it went there. Remember, it was west, so I'm going to keep that as positive. And then we have the 0 meters that doesn't have direction because it's at rest. And then we had the 60 kilometers that's going east. So since that's opposite of west, that's going to be negative. So I'm just going to make that a negative 6.0 times 10 to the 4 meters, okay? And of course I'm going to divide that by the time that I got before, which, by the way, if you didn't calculate it, you should, but that should be 7,200 seconds at 2 times 3,600, and 1,200 seconds, and 2,100 seconds is what you should have gotten for all those calculations up there, okay? And so if I do that, since now I'm basically subtracting, I'm left with a smaller number than I had for average speed, and that is 9.5 meters per second. Okay, make sure you put it through on your calculator just to make sure you get the same answer as me. But remember, that's going to be different. Oh, one other thing. You see that I didn't put a direction on the velocity. The reason is because I already defined west as positive. So if this is already positive, which I mean, we haven't written it, but it is assumed that it's positive, right? Because there's no sign in front. I'm saying it's going west. However, it's not wrong to back here put the west in those square brackets to say that's the direction it's going. Okay? But as long as you've defined a direction as positive and your answer is positive or negative, you're still telling me the direction. Okay? That's that for uniform motion. So let's get on to acceleration in the next video.